this is the last video that I'm recording before starting the class. If there are more videos that you think I should record and you've gotten through them all up to this point, let me know. Maybe I can add a few more of them last minute to the class. But for now, 7.2, last discussion topic in the course notes, which is efficiency of recursive sorting algorithms. Iterative algorithms are kind of straightforward to analyze because assuming you can figure out how many times the loop will go through. Recursive code is a little trickier because you need to not only analyze the running time of the non-recursive part of the code, you also have to consider what is the cost of a recursive call, which is not immediately transparent. In CSC148, Introduction to Theory of Computation, you'll learn how to do this formally, maybe with me, especially if you're taking it in the fall when I am coordinating it. But for this course, we're going to see a nice visual intuition for analyzing a simple recursive function. So here's merge sort. We just saw it if you're watching my video series. And let's suppose that we call merge sort on a list that has some length n, and n is hopefully some number rather bigger than 2, or equal to 2. If it's equal, like, it kind of becomes, like, you can still do these arguments, but it's generally nice to think about it when it comes to a really, really, really big list. Like, imagine you're trying to do a sort, there's a million numbers, what's it going to look like when you do that? Well, to start off, let's analyze the running time of the code in the branch other than the recursive calls. So these lines are not immediately clear how much time it's going to take to do them because, you know, how can you say how efficient your function is when you need to rely on a definition of how efficient your function is, right? Sort of a circular logic problem. So here's what we're going to look at. First off, the divide step. So that's right here. Or specifically here and here. This takes linear time, specifically because, and I should probably jump to this note down here, the slicing happens in the same line as the recursive call, but slicing a list itself is not recursive because technically the way that this line here is run, we don't just jump into the code right away. The first thing that happens is whatever expression is in these parentheses gets evaluated first, and then after that is done, this computation is then passed over to this function. Now, looking specifically at how to divide things, well, it's constant time to calculate the midpoint of the list, but actually slicing the list in half, figuring out, okay, here are all the things in one block, and then here are all the things in the other block, we'll say takes linear time proportional to how big the list is. Merge operation also takes linear time, that is approximately n steps. Why is that the case? Think about it for a bit. Maybe rewatch my previous video where we tried to actually do the merging and think about how it might work if you had a really, really, really long list. How much time is that process of doing those comparisons going to take? The other operations, so length of the list, doing some basic arithmetic, the act of returning are all constant time, don't really matter what size our list is. Putting this together, the non-recursive part of our algorithm is big O of n, linear with respect to the length of the list. But we haven't quite figured out this problem here, the cost of the recursive calls. Well, we do split the list in half, so each one of these calls is going to be on a list where we know the length. The length is going to be n over 2. And each of those is going to have n over 2 steps, as well as 2 recursive calls that are going to be on a list of n over 4 steps, so on and so forth. So we can represent the total cost of this thing as just a big old tree, like the trees that we've been used to learning. At the top level, we have the cost of our merge as our original recursive call. This is the most expensive non-recursive operation we have to do, plus 2 recursive calls of size n over 2, which then in turn have recursive calls of n over 4 each, and so on and so forth. And at some point, n is divided by something big enough that you just end up with ones at the bottom. Now, even though it looks like the tree is showing the sizes of the list that the recursive calls, what it's actually showing is the running time of the non-recursive part of the recursive calls, which happens to be approximately equal to the size of the list. So the height of this tree is something we call recursion depth, the number of times that you have a recursive call before the base case is reached. So if this is your original list that you have up here, you have to do a recursive call to go down one step, then another step, and if you track the height of this tree, that's how many times you have to do a recursive call. Or, if you're visualizing this as a Python tutor, how many of those different vertical frames are actually getting added to our stack. For merge sort, we start with a list of length n, and we divide by 2 until we reach a list of length 1. This means that the recursion depth is how many times you can divide n by 2 to get 1. In other words, what is k such that 2 to the power k is about n? Hey, remember logarithms? Yeah, so this is literally the definition of logarithms. K is about log n, so there's log n levels. Now, note that at each level, the total cost is n. If you add them all up, you got n over 2 times 2 is n over 4 times 4 is also n, right? So, at each level, the cost is n, which means the total cost is n times log n. So our cost that we go with is big O of n log n. This is a lot better, though, than quadratic n squared, n times n, which is selection sort and insertion sort for really big values of n. Now, this analysis only depends on the size of the input list and not the contents. In other words, the way that you split up the list doesn't really have any impact on what the actual contents of the list are, which means that the best case and the worst case, big O running time for merge sort, is the exact same thing. There's no way that you can kind of shortcut the steps here. You're always doing the same thing regardless of the contents, which means you can say it's big O of n log n for best and worst case no matter what for merge sort. Now, what about quick sort? Can we do this same analysis? Not exactly. And the real difference here is that with merge sort, we always know we're splitting it in half as accurately as possible. With quick sort, that's not the case. And we even saw that in our example where the first pivot that we chose was our 8, which was actually the biggest element of our list. We didn't even get close to cutting it in half. We barely cut it at all. Now, suppose you get lucky, and every recursive call you choose the pivot to be the median of the list, which is exactly what you want, and so the two partitions have about size n over 2. Then, hooray, problem solved, it's merge sort, it's n log n time. Great. But what if you're really unlucky? Suppose you always choose either the smallest or the biggest element. So you pick the 1, and then you pick the 3 and the 4, and so every time you're doing it as terribly as possible, then your partitions are as uneven as they can be. One has no elements, and the other has all the elements minus the pivot, and so your tree looks something like this. Yeah, n minus 1, n minus 2, all the way here down till you get to the 2, and there's only 2 things to combine there. Here, the recursion depth, which remember is the height, is n. How many steps you have to go to get from n all the way down to the 1? Well, there's n steps here. So if you add the cost of the levels, you get this expression. You have n minus 1 plus n minus 1 plus n minus 2 plus n minus so on and so forth, all the way down to the 1, which is n minus 1 plus the summation here. In other words, quadratic runtime, n squared. This means for quicksort, the choice of pivot is really important. If you repeatedly choose bad pivots, the runtime becomes horrible. The best case running time, cool, n log n, great. The worst case running time is the same as you saw with your other algorithms, n squared, not so good. Now, you might wonder, okay, well, why would you use quicksort then if it seems like sometimes it can be really bad? Particularly if its worst case performance is worse than merge sorts. Why don't you just always use merge sort? Now, we've been sweeping a few details under the rug as we've been going here. For instance, saying things like merge takes big O of n steps, partition also taking big O of n steps. But the big O expression that we use to describe these ignores constants. So something like 5n and 100n are treated as equal, which they aren't exactly. And especially for small cases, this does actually make something of a difference. In practice, doing this for real, the non-recursive parts of quicksort are generally faster than the non-recursive parts of merge sort. So this means that quicksort has quote-unquote smaller constants than merge sort, so it can take a fewer number of operations and thus performs faster. With some background in probability theory, we can even talk about how to perform quicksort on a random list. of some length. And it turns out, on average, not looking at best or worst cases, but just an average of any possibility, the performance is n log n, with even a smaller constant than merge sort's n log n, which suggests that if you do things properly, actual quote-unquote bad inputs for quicksort are relatively rare. And we'll actually, if you take a CSC148, see this proven in some detail.